Now that we've talked about a direct comparison test, let's take a look at another series here. Let's look specifically at the one I've listed here, 1 over 2 to the n minus 1. Now, if we try to apply the direct comparison test here, it would make sense that we could go ahead and let me just write the a sub n and b sub n terms. That we could write, okay, 2 to the n minus 1, and let's compare that to another similar series. Well, 1 over 2 to the n makes a lot of sense, right? We see that the difference between these two series aren't really going to be dramatically different as n approaches infinity. One just has a minus 1 in the denominator, so they're going to behave pretty similarly. And we already know that 1 over 2 to the n is indeed going to converge. We said that previously in our previous video on the direct comparison test. So we know that this series converges by GST. Now, take a moment and think about an issue that we may have here, because something about this should bother you. And if your thought process is that there's something wrong here, is you're right. We look at this here, which series is actually the larger series? Well, again, this series here has a smaller denominator, which would make the overall ratio larger. And that means this series is actually greater than this series. So let's think about this for a second. If you're, and let me just kind of draw this again, not exactly what's happening here, but I always like to think about these as functions. If 1 over 2 to the n, 1 over 2 to the n, if that series converges, well, what does that tell you about this series here? And the answer is, you're right, absolutely nothing, right? Or I should say, nothing in terms of being able to use the direct comparison test, because just because your smaller series converges doesn't mean you necessarily know what's happening with your larger series. Your larger series could start diverging, or it could indeed also similarly converge. We don't know. So instead, we've got to think about this in another way instead of just trying to use the direct comparison test. And right away, that reveals a little bit of a limitation with the direct comparison test is that while the test itself is actually pretty straightforward and there isn't really much work we need to show, it's limited in that it only really works if you know for certain that your helper series is either smaller or larger, and as a result, either diverges or converges respectively. So let's go back to this problem here. So while we can't use the direct comparison test, let's take a step back and again, look at these two series. I said just a few moments ago that these two series behave really similarly. As n approaches infinity, really, what is this minus 1 going to do to the outputs of the function as the n value gets that large? And the answer is not a whole lot. In fact, as n approaches infinity, these two functions are going to be virtually indistinguishable from one another. They behave the same way. And in calculus, we have a way of describing that, and that's called a limit. We say that the limits of these functions as n approaches infinity should be exactly equal to each other. And so while we should be very suspicious that this series here converges, like we think it will, right? Because we think it's going to do pretty much the same thing that 1 over 2 to the n does, we need a more analytical way of expressing that. And that's where the limit comparison test comes in. And our way of stating that these two limits are effectively the same as n approaches infinity is to look at the ratio of a sub n and b sub n. So in other words, we would look at the limit of the ratio between this series over this series. And if you wanted to flip these around, you absolutely can. That's not going to change your conclusion. What you're looking to see is that that limit is equal to some positive finite value. If that is a positive finite value, then you know that both series either converge or they both diverge. In other words, this series here will do exactly what 1 over 2 to the n does. So let's actually write that out, okay? So let's actually do this problem. So I'm going to assume that you already know that 1 over 2 to the n converges by GST and that you've already written that justification, okay? I'm not going to do it all now, right? Although I might as well. We already just did in the previous problem, but it might as well. I'm going to leave that there. All right, so you know that this series here converges by GST. Our helper series converges by GST. Now, what's neat about the limit comparison test is you don't have to stumble and try to figure out with whether or not that series is larger or smaller, although we do know it is smaller. But you can just go ahead and look at the limit of their ratios. So we would say the limit as n approaches infinity of our current series that we're trying to evaluate the convergence for, or determine its convergence for, divided by the series that we're comparing it to, 1 over 2 to the n. Let me actually move that up so we have a little bit more space to work with. 1 over 2 to the n. Well, we can rewrite that as the limit as n approaches infinity, and I typically like to do this vertically, but I'm out of space. Well, 1 over 2 to the n minus 1 divided by a fraction is equivalent to multiplying it by its reciprocal, so that's 2 to the n over 1. And I'm just going to clean that up and just write it all as one single fraction. So I'm going to move that 2 to the n over to this numerator. So I'm going to say that. So if this is true, now let's think about the limit of this. Well, at first glance, while it looks like we might have indeterminate form, what happens when we divide both the numerator and the denominator, each term in those, by 2 to the n? What are we left with? And the answer is just 1. So the limit of all this is both positive and finite. And what does that tell you? Therefore, this series that we're trying to determine the convergence for also converges by not GST, also converges by the limit comparison test. Okay, and again, it's important that you do make sure you state what is going on with your helper series is either convergence or divergence. Okay, so I'm going to try a couple practice problems right now, but before I do, I just want to kind of highlight some of the differences between the two tests. Each test has its own strength and weakness. I don't want to say weakness, but there's always a give and take there. The direct comparison test is really nice in terms of the amount of work you need to show. Really, all you need to do is come up with a really easy helper series, show that series is convergence or divergence, and then you can just pretty much state by DCT that series is going to do the same. The problem with that is sometimes you have to, again, stumble around with figuring out whether or not that series is larger or smaller, because again, if you come up with a larger series that diverges, that doesn't necessarily tell you anything about your smaller series' convergence. So that becomes a little tricky. The limit comparison test, on the other hand, should always work, right? You can always do the limit comparison test on any problem that you can also use the direct comparison test for. The drawback is that sometimes it does get a little unwieldy. We do have to show a little bit more work, but honestly, after you do a number of these, it's not too bad. All right, so let's try a couple quick problems here. Let's try number 3, just to start off. So there may be some here that you could use the direct comparison test for, but I'm just going to try to focus on highlighting the work for the limit comparison test. All right, so first off, we don't need to sit here and think about whether or not we think this series is going to converge or not. We can just try to come up with a helper series right off the bat. And what I always recommend is to highlight and think about what's going on with the degree of the numerator and denominator. Well, you know that the numerator's degree is n, right? Because when you take the square root of a quadratic, you get n. And the denominator's degree is n to the 3/2. The square root of a cubic is 3/2. So if I were to simplify that, I could rewrite this as 1 over n to the 1/2, or 1 over root n. So that becomes right away a good series to compare it to. So let me just write that. I'm going to say versus, or my helper series, n is equal to 1. I'm going to write this as 1 over root n, right? Or 1 over n to the 1/2. It's up to you. Well, again, I don't know if this is necessarily larger or smaller, right? But I do know that this series does indeed do what? It diverges by the p-series test. How do I know that? Well, because my p-value is equal to 1/2, which is less than 1. Therefore, this series does diverge by the p-series test. Well, now it's time for us to do the limit comparison test, and if we get a positive finite value, I know that my series will do the same exact thing as my helper series. So let's set that up. So the limit as n approaches infinity, and I'm going to write my original series here, or my a sub n, I should say. And again, I'm going to divide it by 1 over root n, which means to multiply it by its reciprocal. So let me rewrite that. The limit as n approaches infinity of And if I multiply this by n, let's just go ahead and distribute that now. That means n squared by n is n cubed. 8 times n is just n, all down in the radical. And again, if I were to divide everything here by n to the 3/2 power, all I need to do is look at my leading coefficients. So what are we left with? This is equal to, let me just write that. This is equal to 1 over root 7. So we need to make sure we state clearly what our limit was. And then we say because this value is both positive and finite, I know that therefore this series that I'm writing out here, n squared plus 8 over root 7n cubed plus 9n minus 1, also diverges by the limit comparison test. Okay? All right, let's do one more example. Let's try to look at this one. And again, I encourage you to pause the video and try this one first on your own, and then check it with Google Classroom, or just wait to see what I'm about to say. So what would be a good series to compare this to? Well, again, I'm going to look at the degrees here, and that gives me a good sense that I want to look at this series instead as a comparison. 3 to the n over 5 to the n, which I know here that my ratio is equal to 3/5, which is less than 1. So this series here converges by the geometric series test. Well, now it's time for us to do the limit comparison test. So as n approaches infinity, I'm going to write 3 to the n over 5 to the n minus 8 divided by the reciprocal of this, which means I'm going to multiply it by 5 to the n over 3 to the n, which then I can rewrite as the following. 5 to the n over 5 to the n minus 8. Well, again, that's equal to 1, which is positive and finite. There's my justification. Therefore, my series, 3 to the n over 5 to the n minus 8, also is going to do the same thing that my helper series does, because that ratio is equal to a positive finite value. It converges by the limit comparison test.